Moving into our lecture, we're going to talk about three-dimensional motion because normal motion is in 3 dimensions. What do we mean by 3 dimensions? Okay, everybody's gone to a movie with 3D glasses probably. 3 dimensions means that it's not just going in one direction. You have motion in multiple directions. And I don't know, I'm just ingrained. So to me, it's just natural. Of course, there's 3 dimensions. You've heard that a lot, but what does that mean? What that means is we can come up with 3 mutually orthogonal directions. What in the world is mutually orthogonal? Orthogonal is the multidimensional equivalent to perpendicular. So, and we'll use the word normal, which is related to that later. So what that means is we can make 3 directions that are all perpendicular to each of the other 2. So I'll take this meter stick, and I'll take another meter stick and make it so it's perpendicular, right? These are perpendicular to each other. Then I take a third meter stick, and I can put that in a direction that's perpendicular to both of the first 2 meter sticks. That gives me my 3 dimensions. Now, the orientation of this is up to my choice, but they have to remain mutually perpendicular. And so that's what we mean when we talk about 3-dimensional space. Traditionally, we'll make our 3 dimensions forward, backward, left, right, and up, down. But they don't have to be. So this picture just is to show, you have fun on the roller coaster, you're moving all around, you're not just going straight forward and backward. It's 3-dimensional motion. And one of the things that we won't use at all today, especially given the time, I'm not going to give you a problem to work because, we don't have time for that. The motion of an object in one direction is completely independent of its motion in a direction perpendicular to that. So if I have an object, this is a bad example, like my tennis ball, and I toss that tennis ball, its vertical motion is completely independent of its horizontal motion. So if I throw it, and I just throw it to the corner of the room, if I throw it, it was going up and down exactly the same as it would have if I'd thrown it straight up. And then it was going horizontally in a different manner that we'll work with these problems starting Friday. But the 2 directions of motion were independent. And so we'll be able to solve the problem as if it's 2 separate problems, one the vertical motion, one the horizontal motion. And what they have in common is the time when they left my hand was the same, and the time when they hit the ground was the same. And so they'll have the same time for both the vertical and horizontal motion, but they'll have different initial speeds in each direction and different accelerations in each direction. 2-dimensional, okay, let's just skip over that. You had reading quiz questions that dealt with some of this 2-dimensional motion. Why? Because that's the topic of the day. And so here's an example. You walk 9 blocks east, and then you walk 5 blocks north. What's the distance that you traveled? 14 blocks. 9 plus 5 is 14. That was an easy question. What's the displacement? Okay, then you use the Pythagorean theorem. So we would say, please work today. Nope. I have not figured out why some days it works and some days it doesn't. I will spend more time trying to figure out that aspect. So if you walked 9 blocks one way, 5 blocks the other, because those are perpendicular to each other, we can apply the Pythagorean theorem. The Pythagorean theorem only applies if you have perpendicular directions. And so I have to draw. Nope, that's not it. At least we're halfway through the slides. That's the same one I just pressed, isn't it? Well, okay. Screen, white screen. I should be able to draw on this. I'm going to go to a different app just so I can draw.
So we had 9 blocks, 5 blocks. It is vitally important that this is a right angle. That's how we integrate a right angle, or 90 degrees. And in that case, the displacement is found by using square root of 9 blocks. I'll put BK for block squared plus 5 blocks squared. 9 squared is 81, 5 squared is 25, 81, 25 is 106. And so I'm going to have the square root of 106 blocks squared. And I see James has a calculator out. Do you have an answer, James?
10.30.
Okay, so I'm going to put 10.3 blocks. How many sig figs do I have? If I go strictly by sig figs, I only have 1 sig fig there. And so I would say 10 blocks. Because 10 blocks, that 0 is ambiguous, but would be not significant there. So that's how we find the distance travel, or not distance travel, the displacement. There's another important thing here. What about the direction? How do I find this angle? I'm sure some people know the answer and are being quiet. It's going to involve a class that's not required, but that we have to know some things about: trigonometry. And so we'll look at our trigonometric functions that apply to right angles. For a right triangle, a right triangle means a triangle that has a right angle in it. We have sine of some angle. By tradition, we use the Greek letter theta, that's th in the Greek language, is equal to the opposite side over the hypotenuse. Well, that requires some new language. So let me draw a right triangle and define what those are. There's a somewhat better right triangle. Here's the right angle. Here's the angle theta that I'm looking for. So opposite is the side of the triangle that is not making up part of that angle. So two sides are making up part of the angle. This one here is not making up part of the angle, so that's the opposite side. One side is the hypotenuse. The hypotenuse is the side opposite the right angle. It's also always the longest side in a right triangle. And it's not defined for a non-right triangle. So this side here, opposite to the right angle, is the hypotenuse. And then the remaining side is the adjacent side. It's adjacent to the angle and not the hypotenuse. And so sine theta is the opposite over the hypotenuse. Then we have cosine theta is the adjacent over the hypotenuse. And finally, we have tangent theta is equal to the opposite over the adjacent, which is also conveniently enough equal to sine of theta divided by cosine of theta. So looking at the triangle that I have, I've now calculated all three of the sides. I used the Pythagorean theorem to go from opposite and adjacent to getting the hypotenuse. It's best practice to find the angle from the two sides that I didn't have to do a calculation on. Why? Because then I don't have any risk of throwing away information in the calculation. So the best practice would be to use the 5 blocks and the 9 blocks. Which side of the triangle is the 5 blocks? It's opposite. And which side is the 9 blocks? So which trigonometric function is going to relate opposite and adjacent? Tangent. So I'm going to do my calculation here. Tangent of theta is equal to the opposite side, 5 blocks, over the adjacent side, 9 blocks. and then I have to put that in the calculator. Now, one more thing to be cautious about. Your calculator has different ways of measuring angles. It could measure in radians, something that we're going to become intimately familiar with before the end of the year, or degrees, something that you're probably much more comfortable with now. So make sure you know which one you're using, because if you use the wrong one, you get the wrong answer. So has anybody calculated what that angle is? How many?
29 degrees.
Okay, so 29 degrees. So now I can say the displacement, which is a vector, is 10 blocks at an angle of 29 degrees. And I got to go back to the picture to remember what directions I had specified on that picture. Really go there. So that was north. So at 29 degrees north of east. So I know this is crazy, but I'm going to try to write again. Pen. You know, I saw somebody recently who disagreed with that common thing they say that Santa, oh, it was chapel. You all saw it, right? Because you all go to chapel. I've got a good feeling. It was false, but it was a good feeling. Forget it. The displacement is 10 meters at 29 degrees north of east. The direction needs to be specified, not just with an angle, not just 29 degrees, because the 29 degrees can be measured anywhere from in any direction. So 29 degrees north of east, the of east says my starting point is east. The of means that, north of means I will go from that east and go north, 29 degrees. Now, we've already talked about vector addition. Vector addition, you add tip to tail. And we start off just talking about, like when I was a kid, the number line, adding numbers. And that's how we add vectors tip to tail. So this is showing vectors A, B, and C added tip to tail. The resultant, the answer to these, is going to be a line starting at the end, going to the beginning. So this actually is the problem that I had set out for you to do. I will, or no, it's not. Excuse me. The problem I had was, yes, 3 vectors adding together. It was these 3 vectors adding together is the problem I had for you. Here is an example. How do we subtract numbers? Subtracting numbers is like adding a negative. If I want A minus B, all I have to do is reverse B and then add it. So I can do, okay, I'm actually going to write this down so I don't forget stuff because I have to change because I can't write on this today. Okay, so going to where I can write. To add those 2 vectors, I had a vector was 27.5 meters at 66 degrees north of east. B vector was 30.0 meters at 112 degrees north of east. And I want to add or subtract those. So A minus B, doing it graphically, I had A was like this, and B was like this. And so A minus B is going to be A, and then I put so I did the A vector plus the negative B vector. I just reversed the direction of B and then added it as normal. And so my resultant is like this.
Now since I'm doing everything multiple choice, I guess for the first exam, I won't be able to say you must add it graphically. I didn't think about that. I'll just have to have problems to say, is this right or is this wrong? Or which picture is correct for showing vector addition. What you generally want to do on a test is to do it what we say is analytically, to take these vectors and break them up into their components. Components, the things that make up the whole. And so if we're going to do that, the first thing we have to do is define our component directions. So I'm going to define, and you should always indicate an x and a y direction. And then I drew from the base of my A vector a line parallel to the x direction, and from the other end, a line parallel to the y direction. Now, my vector can be made up of the sum of those two, so that's a x and a y. The portion of a in the x direction, the portion of a in the y direction. And the angle between this is 112, looking at the wrong one, 66 degrees. And this was 27.5 meters. So now the trick is, what is AX? In my triangle, I know two things. I know an angle, and I know the hypotenuse. Which side of my triangle is AX? Adjacent side. So that means I can take the trigonometric function that relates adjacent and hypotenuse. That was cosine. So cosine of 66 degrees is equal to my adjacent side a sub x over the hypotenuse 27.5, I believe it was, yeah. Well, we know everything in there. A of x is equal to 27.5 meters cosine of 66 degrees equals, and given that I only have 4 minutes left, well, I see Sarah is going fast. Do you have the answer there, Sarah? It's what? 11 point, okay. Now I'm going to keep an extra digit here. I don't want to throw away information too early. Even though it only had, in the angle, I don't know if it had 2 or 3. You don't use sig fig rules with the angles when you're using trig functions anyway. Likewise, if we want to find the y component, the y side was the opposite side. So sine of 66 degrees is the opposite a sub y over hypotenuse. So a sub y is equal to 27.5 meters sine of 66 degrees. What's that? 25 point what? 12. So there I've broken my A vector into its components, its horizontal and vertical components, or its X and Y components. Now I would normally do the same thing for the B vector, and then I just add like components. I add my X components together and add my Y components together. Or if it's a subtraction, I would take my AX component minus my BX component. As my high school algebra teacher taught us, we add apples to apples and oranges to oranges. You can't add apples with oranges. You can't add the X component to the Y component. We add all the X's together, and separately we add all the Y's, that whole independence of motion idea. And then we have a final triangle when we've added them together that has a horizontal, a vertical, an X and a Y component. And we combine them again, just like we started to use the Pythagorean theorem to find the magnitude and tangent to find the direction. As an aside, my high school physics teacher died yesterday. That's the reason I'm here. So that makes me sad. His wife was the algebra teacher who taught us that apples and oranges thing that I said. So it's kind of a sad day for me. I am going to stop the lecture there. Your homework will be dealing with doing vector things like this. I will go and recheck the homework to make sure that it's only vector things, because I obviously had a little more I planned to do in today's lecture. So have a great day.
Nathan, don't leave.